Good evening, everyone. On behalf of the IT and Computer Sectional Committee of ISL, I would like to welcome all of you for our public lecture. As IT and Computer Sectional Committee, we conduct several activities to fulfill our main responsibility of popularizing computer and engineering and as well as IT in Sri Lanka. Further, we also support key activities of ISA, and as part of that, we do a lot of sessions at Techno, and we do a lot of competitions at Techno, like IoT competitions and robo games, which is mainly based on robotics, and also Idea Challenge. And also, as a part of our activities, annual activities, we conduct several public lectures. Mainly on the technical or engineering related lectures, and as well as we are conducting seminars as well as workshops for the benefits of young graduates who are passed out from Motu University, as well as the practicing engineers to enhance their knowledge and help them to keep them up to date with the latest technologies and the developments in the industry. As a part of that, we are doing these sessions, the evaluation of application development from apps to services and APIs to microservices. This is the second session of the 3-session series. So these sessions will be conducted by Nilesh. He's a principal software architect at a Platformer Cloud Private Limited. It's a Google partner company in Australia, and he's an authorized Google Cloud trainer and a Google Cloud certified professional, cloud architect, and a certified Kubernetes administrator as well. He's a community lead of Communities Sri Lanka community, and he's a public speaker for many technologies around the cloud, as well as Docker, Kubernetes, and microservices and other related networks. I think he has more than 7 years experience in this field. I think he's one of the best person to talk about this, the evaluation of application development from apps to services and API to microservices. Over to you, Nilesh.
Thanks, Laksara. Thanks for the introduction. Can you guys hear me okay?
Yes, we can hear you, Nilesh.
All right, okay. So I'm gonna share my screen. Can you see the screen?
Yes, we can see.
Okay. Right, okay. So, yeah, so thanks, Laksara, for the introduction. So today I'm gonna talk with you guys about modern DevOps and how containerization and orchestration comes into place. So in the TOC, I'm gonna do a small recap of what microservices are, what we discussed last time, and then I'm gonna jump into containerization and orchestration. Then I'm gonna talk a little bit about how CICD comes into place, and then with CICD testing and continuous monitoring with CICD. And then I'm gonna take a stop at deployment methods, and then we can sort of like do a Q&A and then answer your questions or whatever you have. Also, before I start, I have to tell that, I'll be covering the concepts here. So basically, this is not going to be sort of like a Kubernetes tutorial. So that's something that you probably will have to learn on yourself. But I will be giving you the basic concepts and why Kubernetes and, all of those things for you so that, you know where to look and sort of like implement the technologies that I discuss in your organization and in the projects that you have. So as a recap of what we did last time, we spoke about the journey of an application from monolith to microservices. So quickly looking at the overall architecture, you can see that on the left-hand side, there's a monolithic architecture where, you have the user interface, business logic, data access layer, all in one as one application, and it's connected to a database. Like imagine an ERP system like this, And then whereas in the microservices architecture, it's different. You have the authorization module as a separate service. You have shipping module as a separate service, billing module, inventory, finance. You know, I'm talking about ERP here. So we can break these into separate smaller services, so that these services are loosely coupled. So even if one service goes down, doesn't matter. It won't affect the others as long as those are loosely coupled. And then you have the flexibility to sort of like choose your own databases. Like for shipping, it would make sense for you to have a relational database of handling payments, but sometimes for something like inventory, you might want to have a NoSQL database. So you have the complete flexibility. Some of these services can be written in Java, some can be written in .NET, some can be in Python. It doesn't matter. So it allows you to be more flexible with your architecture and implement things in a way that you have never done before by using a microservices architecture. Also, another advantage would be like the scaling capacity of a microservice architecture compared to a monolithic architecture, where you know in this scenario, to run the entire ERP solution, that serve request percent, this entire ERP solution, you need about 4 GB of RAM and 2 CPU. So in a scenario where you need to sort of like manage like for example, let's say that for shipping module only, you get about 2000 requests per second. That means you have to sort of like scale the entire application uh, to sort of like support that number of requests, right? But in this scenario, it's different. So here, the shipping system might only need about 500 megabytes and half a CPU to run to handle 1000 requests per second. So you only have to scale that bit rather than you scale the entire thing. So you can selectively scale certain components in your architecture in your application when it comes to microservices, which is sort of like more efficient. Um, than running monoliths. And also there are other things like maintaining code quality, less defects, upgrades, and all of those things. There are a lot of things that we discussed last time. So yeah, I think that's a good recap of what we discussed last time. So now today we are going to talk about the first thing: why does software break in production, right? So if you guys are developers, if you guys are developers like me, I remember back in the day, at the end of the sprint on Fridays, I would, merge my code to master. I would, I would do a deployment on the QA environment, and I would just, happily go home. And on Friday night only, the QA guys start working usually. So they would be testing the new release on the QA environment, and then all of a sudden, I would be getting emails from Jira, bugs and all of it, saying this component is not working. That is wrong. Blah 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 blah. So there are issues. As you can see on the sort of like a meme here, says that what a developer would usually say with this happens is that sometimes we say refresh the browser, log out and log in again, uh, and then finally we would say, but it worked on my machine. Yeah, it works on your machine because your machine um, is you have all the libraries and all of it, and everything just works together in your machine. But that would not be the case sometimes when you do a deployment on the cloud or in a Linux server, which is a separate environment. So sometimes some of the libraries may be missing. I remember there was this node module that was working very fine with the Mac OS, but there was a problem with Ubuntu. um, it was actually trying to use the curl command or something. I can't remember exactly what, but it was working fine on my machine. But when I did the deployment in the server, it didn't work. I had to sort of like install some libraries on the operating system itself for it to work properly. So there are things like that. So this is the main reason why software breaks in production. But imagine if we can sort of like ship the entire solution from my which works in my machine exactly like that into the cloud, into whatever the environment that we want. So that's where containerization coming. So containers are like the solution to the problem of how we can get software to run reliably when moved from one computing environment to another. It's very portable. If it works on my machine, it would definitely work on yours or whatever the other machines, with the exception of Windows sometimes. So I'll come to that in a bit. Um, so when it comes to containers, people immediately jump into the word Docker, right? So it's like how we say, back in the day, we would say, we would call toothpaste Signal, or we would, call slippers as Bata, right? And it's different, right? Signal is a brand that, produces toothpaste. Bata is also another brand that produces slippers. Same with Docker and containers. So containers is a concept, uh, containers is a technology, and Docker is someone that actually implemented it. So actually, Docker was like, it's like this. So back in the day, I think this was 2014, if I'm not mistaken. The concept of containers existed in the Linux system, Linux kernel. So how containers is, you know, uh, how containers works is in Linux, there are C groups and namespaces. So with namespaces in Linux kernel, you can sort of like isolate a process and make it have its own file system sort of a thing. And with C groups, what you can do is, for this isolated process with its own file system, you can sort of like set CPU and memory limits, right? Sort of like an internal, sort of like a small virtualization. Okay, that's what containers are, which existed on Linux kernel, I think from 2005 onwards, if I'm not mistaken. Um, but it's very hard to implement that. So what the guys, the Docker guy or dot cloud, I think back in the day they were called, what they did was they made it easier for us to sort of like create containers in Linux subsystem, in Linux system, and then manage them in a much easier way with the Docker CLI, right? So that's what Docker did. So the runtimes or the engines that allow us to sort of like create these containers and run them, we call them container runtimes. So there are two kinds of container runtimes. The first one, we call it high level container runtimes and low level container runtimes. I'm just going into a little bit of detail here. So high level container runtimes are the ones we directly access. So we would talk with high level container runtimes, and the high level container runtimes it work with the low level container runtimes, and the low level container runtimes it work with the kernel to sort of like actually implement the things, right? So we don't need to know more about low level container runtimes because it's behind the scenes. So we need to know more about high level container runtimes. So containerd is the most popular one. So if you have known like Kubernetes and a lot of even Red Hat Linux is dropping support for Docker. But Docker is written on top of Containerd. So Containerd is like the high level container runtime. You can use Docker on your machine. It's very easy to use. So it doesn't matter you use Docker or Containerd or whatever. It's still the same. So you don't have to worry much about it. Then there's another one called RKT. I think that's deprecated now. And there's another popular one that Red Hat and everybody is sort of like pushing forward called Cryo Engine. But at the end of the day, all of these are container runtime engines. We can use whatever that we like, and then when at runtime, these would have different performance stuff. It really doesn't matter for us as developers. Like for more reference, I have added a link here. You can actually visit this and then read more about container runtimes on your leisure when I share the presentation slide deck with you guys. So moving on, containers versus virtual machines. So we spoke about namespaces and all of it, but in a nutshell, if we look at how containers and virtual machines work, like we all know what virtual machines are, right? So what virtual machines are is you have infrastructure. On top of like the physical infrastructure, you would have a hypervisor. On top of that hypervisor, we can dedicate CPU and memory virtually, and then create operating systems on top of it. Like I remember if all of you were undergrads at some point, you probably had to run Linux on your laptop or your desktop, right? You installed Oracle, VMware, VirtualBox or something, and you did it. That's like one example of how VMs work. So here you can see that in this scenario, we have sort of like three virtual machines. And you can see that on these three virtual machines, there are three guest operating systems installed. So in this scenario, this is, let's say this is running Ubuntu, this is running CentOS, and again Ubuntu. So you know that for an operating system, normally there's a minimum requirement to run the operating system services. So let's say that to run Ubuntu system services, you require around 500 megabytes of RAM and half a CPU. This one also for CentOS, let's say 500 megabytes and half a CPU. And here also 500 megabytes and half a CPU. So just to run these three virtual machines and run these three operating systems, we are immediately wasting about 1.5 GB of RAM and 1.5 CPU from our physical infrastructure, just to run the operating system on all of these three, right? On top of that, only we have the left are allocated to our application. Okay. But in this scenario, if you look at containers, it's a bit different. We have our infrastructure or the physical layer, and then we have our operating system here. Let's say Ubuntu is running here with 500 megabytes of RAM and half a CPU, utilization of resources. And then we have the Docker engine running on top of it, Docker or whatever the container runtime engine you have. And then on top of it, we have the applications running. In this scenario, we can fit in more applications to this infrastructure compared to this one. Hypothetically, in this scenario, we can only fit three here, but here we were able to fit six because, there less resources were consumed for, running operating system and all of it. So we can fit more applications in this singular VM. If you guys have any questions, you can actually ask on the chat or just unmute and ask. It's fine. Right. Okay. Right. Up to this point, do you have any questions? I can't really see the chat. If somebody can read the chat, if there are any questions.
Nilesh, there are no questions as of now.
All right. Okay. Right. So I guess people know this stuff there. Uh, all right. So to simply put, uh, it's like this. The applications on your machine running as containers would look like this. This is taken from the movie Finding Nemo. So as you can see, the water is like your infrastructure or like your resources, CPU and memory. And the containers are the bags, and the applications are running inside these bags. And it's pretty cool because you can see, like, for example, sorry, for example, in the same machine, now you can run a Java 12 app or Java 11 app and a Java 8 app or Java 7 app. You can run a Python 3 app and a Python 2 app without going into these virtual environments and stuff. You can run a Node 10 app and a Node 14 app without having to use NVM and all of it, because each and every container would have its own file system, its own libraries, and all of it together bundled as a container. It's not going to affect your outside machine, whatever the libraries or whatever the things that you have installed. So there's 100% isolation here, that you can actually have different development environments and then run these applications on the environments that suits these applications. Yeah. Okay. Like, for example, you cannot, in this scenario, you can run a PHP I don't know, that's PHP 8 now, right? So PHP 5.5 and PHP 8 on the same server. You can do that. Right. So let's come to the modern standard, how containers and VMs work together. So that's another thing that I couldn't tell you here. So this was great, right? But now let's think about AWS, Google, or Azure. None of these people are giving us a container, right? We can create virtual machines in Google Cloud or AWS or Azure. We can create virtual machines, and we don't get to create containers there. I mean, they have specific services like ECS, etc., that allows us to create containers. But to sort of like the whole VM scenario where we want to install Ubuntu and do something, they don't give us a container for that. They give us a VM for it, and there's a specific reason why. Although we say that these VMs are, you know, uh, not as resource efficient as containers, uh, it's a multi-tenant scenario. So if this is the AWS infrastructure and they have the hypervisor, and if I'm asking for a VM and if you are asking for a VM, that's fine. In this scenario, this is completely isolated. I cannot hack into you, you cannot hack into me. But imagine a scenario where um, the AWS infrastructure is here and the operating system is there, and there's Docker, and then I'm asking for a container, and then you're also asking for a container, right? Now, both of us have shell access. So you can easily exploit a vulnerability in the operating system and attack the other application if you there are possibilities that you can do that, right? So it's a bit less secure to have a multi-tenant situation running as containers. So containers should be always single tenant to be more secure, right? So taking that into consideration, that's what the cloud give us. So cloud would always give us VMs. So when cloud gives us VMs, so on the VMs we would install Docker or whatever, and then on top of that we would run our applications uh, together, so that we can, our application is portable now. The application and the binaries, all of them as bundled into as one as containers, and we can run anything on our containers on our VM. So that's how it works out in the modern world. Right. So basically, the bottom line here is like, if you have a data center, you would still have your infrastructure, you would still have your hypervisor, you would still create, you would have VMware or OpenStack or whatever running here. You would still create VMs, and on top of those VMs only you would have Docker, and then running your containers there. So that's how it works out. Um, so moving forward, we spoke about microservices. A big application would have about 10 or 50, I mean, 10 plus, I'd say 10 plus microservices. Depending on the size of the application, it can be 50 microservices, it can be 10 microservices, or, way more than that, depends. So let's take a small application where, it has about 10 microservices. So these 10 microservices can be, run easily as containers now, rather than, creating 10 VMs to run these 10 applications. You can run a few VMs, like 2 or 3 VMs, and then run those 10 applications as containers scheduled on those VMs. So that's what you can do with containers. And right. So the next question is, now when you have 10 microservices and you have 10 containers for those microservices, and let's say that you are scaling these microservices, right? One component is scaled into 10 replicas, another component is scaled into 5 replicas. So likewise, you are scaling these things. So all of a sudden, the number of containers are going to grow massively in your system because you are scaling them now. So it's gonna easily go up into 10, 50, 100, etc., right? So when that happens, uh, it's not humanly possible for a singular person to actually manage it using something like Docker CLI or something. It's very hard for you to manage about thousands of containers, right? On your own. There are so many things you have to decide. You have to see, you have to understand where to sort of like deploy this container. Yeah, you have a bunch of VMs, like where to schedule these containers, like keep watching these containers, and if something happens, reschedule them on a different node and all of it. I mean, it's humanly impossible to do that. So yes, so that's where orchestration comes in. So how the orchestration works is we are basically going to tell the orchestrator, hey orchestrator, look, I want to run my Java application. And I would sort of like give my orchestrator what, hypothetically, let's say that the orchestrator, I'm saying that, okay, I have three virtual machines. These three virtual machines are for you. So I'm going to give you commands, and then you are going to, take the best decisions, and then do the stuff for me, automate the stuff for me. And then that's what the orchestrator would do. So basically, I would give my orchestrator three virtual machines and tell the orchestrator, hey orchestrator, I want my Java application to run. I need it to be scaled into 2 replicas. And to run my Java application requires about 500 megabytes of RAM and one CPU. So when I tell those things to the orchestrator would look at these nodes, and it's going to take a look and see what are the nodes that have available resources to run my application. And it's going to schedule my application on those nodes. So that's what we call by resource allocation and scheduling. And we can also tell the orchestrator, hey, orchestrator, keep watching my application. And if there's a high traffic coming, or like I can give certain rules. And then automatically I would tell my orchestrator, if something like that happens, you start scaling my application. You make replications of my application. And the orchestrator would do exactly that automatically without me having to do anything specifically on the time that high traffic comes. It does load balancing also automatically when I scale my application and all of it. Uh, you don't have to manually go and create load balancers, and all of those things are not necessary. The orchestrator takes care of it and then provide you single endpoints, so that when you hit those endpoints, it's automatically gonna uh, distribute the traffic to the number of replicas you have. I think Java developers have something like Eureka, etc. Other people probably use something called Console. All of those things are not necessary with an orchestrator, because they do the traffic management and the service registry and all of it automatically within the orchestrator itself. So we don't have to create another layer of something like Eureka, where you do service discovery, load balancing, and all of it. It's not necessary. Uh, it also manages the network and access. You can set up firewall rules. There are so many things that you can do. And then it also tracks state. So this is very important. If your application crashes, the orchestrator would know that your application has crashed. It would automatically sort of like restart your application. Or like if one of these VMs go down, it would know, and then it would automatically reschedule your applications into the other VMs. So it sort of like takes care of the availability stuff, tracking state, and a lot of things are automated, so that the system engineers or the DevOps engineers can easily go home around 5 p.m. and then have a good night's sleep without having to you know keep looking at the system monitors, and uh, or pray to the servers before going home or for a vacation, because the orchestrator actually eases a lot of things up for you, and then also streamlines a lot of things. Right. So we spoke about orchestrators. So when we talk about orchestrators, so there's only one thing that comes into mind, that's Kubernetes. But Kubernetes is not the only orchestrator in the town. There are a few others as well. So one of the most other popular ones is called Docker Swarm. Uh, and there's HashiCorp Nomad, and there are a few other stuff as well. But hands down, Kubernetes is sort of like the winner, that everybody's sort of like adopting these days, and has a huge community. And I'll tell you why. So the reason why Kubernetes is very popular is because it was originally designed by Google, and then now currently it's maintained by the Cloud Native Computing Foundation. It was donated. It's open source, and Kubernetes was sort of like uh, used in Google to run Google services even before Docker was introduced. So even before the concept of Docker containers were introduced to people, Google had this thing called let me contain that for you, sort of like another technology similar to Docker that would use the whole Linux C groups and namespaces to create the containers and then run them. So this Kubernetes project, it was called Borg back then. Uh, Borg was used to sort of like run and manage Google's services, all the Google services back then. And then Docker was open source, Docker was introduced to people, and then people were getting into containers. So Google knew that when people were getting into containers, people are going to run into the problems that I discussed earlier, right? Managing thousands of containers in production is going to be hard. And then a need for an orchestrator would be, people would need it. So that's how Google open sourced Kubernetes. At the same time, Docker guys also knew this is going to happen. So Docker guys also did a project called Docker Swarm. But when Docker Swarm and Kubernetes both hit the market, Docker Swarm was not mature because it was very early. It was not battle tested. But Kubernetes was battle tested because it was running Google services for about 5+ years. So it was more mature. It had less bugs. And then the community sort of like went with Kubernetes, and then community started contributing towards it. And then more features were developed, and right now it has a huge community fan base, and everybody is adopting Kubernetes. And like all of your problems, all of your issues, there's always a solution with Kubernetes. If you go with something like Docker Swarm, you might even not find solutions to the problems you have even in Stack Overflow. So that's how Kubernetes has become the clear winner in the container orchestration race. But still, some people do use Docker Swarm, but a lot of them are using Kubernetes because of the community support and everything that it provides. Um, so I'll just slowly tell you the Kubernetes architecture. It's nothing much. To run Kubernetes, you need there's something called a master node, and then there are stuff called worker nodes. So you can have any number of worker nodes that you want. So these are like the nodes that would be running your containers. And then master node is sort of like the node that's the brain of Kubernetes. That like this is where we tell, like, hey master node, run my Java application, and then the master node would sort of like look at the available nodes, and it's going to see, all right, so these are the nodes that this Java application can be scheduled, and it's going to deploy the applications accordingly. So these are the components. Basically, etcd is like the Kubernetes data store. This is where it stores the configuration. API server is where we talk to Kubernetes. This is the interface. So when we want to tell, hey Kubernetes, run my Java application, we are going to talk to the API server to do that. Schedule and controller manager are the ones that actually decide where our containers should be scheduled from the nodes that are allocated. And controller manager is the one that keeps looking at our running containers and tracks the state of the containers. So if something is crashed or something is not going according to plan, controller manager would know, and it would automatically take action to sort of like fix it. I mean, you don't need to know this to sort of like work with Kubernetes. I'm just telling you, just for your understanding. And for each and every node, you have something called kubelet. So this kubelet is the one that actually does the work. So basically, when we tell the master node, right, run my Java application. So if it decides this node, it's gonna communicate to kubelet saying that run a Java application here. So this kubelet would do the Docker run, and it's gonna, this kubelet is the one that is gonna spin up a container in this particular node. And what this proxy does is it actually creates a network internal to Kubernetes, a virtual network across all of these nodes, so that a container in this node can communicate to container in another node, right? With the IP address, it has a DNS and all of it. So, I mean, it's pretty amazing. Just Google Kubernetes or in YouTube, or just follow a course in Udemy or something that actually teaches how Kubernetes works. So it's just sort of like an overall functionality explanation on Kubernetes. Right. So with Kubernetes done, I'm going to move on to CI/CD. Do you have any questions on up to now?
There was one question from the chat box. The question was, Nilesh, is Zookeeper is an orchestrator?
Right. Okay. Yeah, by Zookeeper is not a content orchestrator. Zookeeper is more like a service orchestrator, right? So the functionality is a bit different on Zookeeper and what Kubernetes does. Kubernetes is written specifically towards managing and orchestrating containers. Uh, Basically, and then the whole DNS, the service discovery, and all of it end-to-end running microservices. Whereas Zookeeper is sort of like more general use, sort of like distribute your services and run them, schedule them, and all of those things. I haven't worked much with Zookeeper, but that is my understanding of what Zookeeper does. Anyone else in the community can correct me if I'm wrong in that analogy with Zookeeper and Kubernetes. Right. Any other questions?
We can continue, Nilesh.
I think there's
There's
another
one more
question.
question. Can orchestrator lead to?
All right. So the next.
Yeah. Can orchestrator lead to? The question was, can orchestrator lead to a single point of failure?
No, it won't. So it won't. It won't. So hypothetically, let's say that in this scenario, my containers are running in these nodes, and the master entirely goes down. But my containers, the processes would still be running. The kubelet won't be managing it. My processes would still be running, and my application would still be, the request would be still be served. And there are situations where you don't actually have a single master, but you sort of like have 3 node masters or 5 node masters to sort of like handle the high availability. So there are architectures that you can implement to avoid single point of failure sort of a thing. So no, so the entire orchestrator with Kubernetes, it's not designed to do like that. Yeah. It's so you can always set up a highly available one, and then you can avoid the single point of failure issue. This is just a basic architecture. Right. So is that all?
Yes, Nilesh, we can continue.
Right. So the next thing is CICD. So so like CICD is like pretty important for a lot of organizations. When we talk about metrics, like for successful organizations, they say that successful organizations deploy, patch their applications in production on a daily basis. Whereas mid-range or sort of like slow-paced companies patch their production systems sort of like on a monthly basis, right? So if you want to be a successful company, you need to have faster releases, faster patches, and you need to do all of them seamlessly, so that your users don't know that the new softwares are updated and all. Everything just happens automatically, right? That's what CI/CD allows us to do. A lot of automation and less manual work. So a typical CI/CD pipeline would be like, you would code, you would commit to whatever the repository can be, GitLab, GitHub, Bitbucket, or whatever, some repository. You probably would go through some checks here. You would do a build. So I'm talking here specifically with related to containers. So when you do a build, you would put all your application artifacts and all of them together and do sort of like a Docker build, a Docker image, and then you can sort of like publish that image into a Docker registry. And then you can run unit tests on your code. You can run code analysis with something like SonarQube. You can run integration tests on your code with the other microservices and whatever. So after running the tests and all of it, now you have tested your code, you have tested your image. Now you can actually push it to sort of like whatever your environment. You can push it to your development environment or the QA environment, And from that, you can promote it to a staging environment, which is sort of like identical to production. And then from staging, you can deploy to production. At all of these points, it's a best practice always to sort of like build once and deploy on other environments rather than building separately towards different environments. Like I have seen a lot of people do this. So what a lot of people would do is, like, especially Java developers, they would build separately for production and they would build separately for other environments like staging, development, etc. Like they would hard code or burn the property file into these Docker files, Docker images, and then build specifically for environments. But that shouldn't be the case. There's this concept called 12-factor applications. So if you follow those concepts, usually what you should do is, like, at the end of the day, the code and everything is same, only the properties change, right? So you should write your application in such a way that you would load the properties at runtime rather than at build time. So because at the end of the day, the only difference between staging and production would be the database credentials and few others, right? Nothing else. So technically, the same image on staging, you should be able to write on production rather than building a new image for production. So, those are the things that you need to sort of like streamline on your CI/CD pipeline if you have a CI/CD pipeline, or if you're planning to do one. Um, so advantages, as I said, right? Rapid releases and gives you minimum human involvements, which gives you less, makes your pipeline and makes your releases less prone to human errors. It also allows you to do versioning and rollback. So every time you do a new release or a new build, in Docker images, you tag the image on Docker registry. So if something goes wrong, you can easily roll back to a previous version without without an issue. So the rest are just explains themselves, like reducing the cost, faster feedback, improving quality, and all of it. In a nutshell, CI/CD looks like this. So you can sort of like plan, you would code it, you would build it, you would test it, you would deploy it, and then you would sort of like manage your deployment at runtime in production or whatever. You would monitor it, and then you would look at the bugs, or you would see, and then again you go back to planning, you would patch it, build it, test it, deploy. So that's how the cycle goes. Um, so the source control, I mean, these are pretty basics. I just included this so that some may know, some may not know. But ideally, how source control would work is, you would have sort of like a stable branch. Typically, this is the master branch or the main branch. And then for each and every feature, we would sort of like go with the feature branch. Like we would break into features. We would also have another branch called development branch, or a similar branch like that, which would have less stable code there. So in that, we would have sort of like features. So once the feature is done, we would merge it to sort of like the development branch, and through the development branch, we would sort of like create a release branch sort of a thing, that, and there in that branch, we would do some fixes, we would do some testing, and then we would merge it to the main branch. And then finally, we would do something called a git tag when we are happy with the code, to sort of like deploy it into production or whatever, right? So that's how source control normally works. But different organizations have different strategies. This is like the most common strategy that a lot of people would use. Some even break rather than features. They would break by sprints. Like this sprint, all of us are coming into this branch rather than going feature wise. So it depends on the organization basically. Um, and then the CI/CD starts here. So the source control have hooks. So in hooks, webhooks. So the way a CI/CD pipeline would be triggered is when you do a master push, the branch push, or when you do a tag push. We can say when we do a master branch push, automatically scan our code to SonarQube or something, test it, do the unit test, all of it, and then provide those checks. We can say when you do a tag push, automatically run the CI pipeline, where you would do the build, you would do the test, and then you would do a deployment to whatever the environment we specify. So so that this is the place where CICD starts. Then you have the builds. So in these builds you have version control, and then when you build an image, you would push it to an artifact registry like a Docker registry. I mean, Java developers know JFrog, so there are other artifact registries as well. You can do those things during the builds. Specifically talking to about Docker, Docker has something called multi-stage builds. So what a multi-stage build allows you to do is basically it's a best practice to always keep Docker images small, but sometimes at build time, that might not be the case. You might have to have a lot of libraries, a lot of things in your image to sort of like build your application. But to run it, you don't need. For example, let's take Node, right? If you're running an Angular or a React application, to build an Angular app or a React app, you need to have Node modules installed. You need to have a whole lot of things. But once you build it, it's just a bunch of HTML, CSS, and JS files, right? You can easily take those out and then put it in a smaller image with which has Nginx or something, and then run it there without letting go of all the Node modules and all of it, which makes the image bigger and more vulnerable, right? So that's how multi. You can also do build time arguments. You can sometimes when you do builds for multiple environments. For example, I said you build once and deploy to multiple environments, right? But sometimes that could be problematic. Like sometimes you might have to build your application in such a way for development with debugging enabled, and then sometimes you have to build the production separately with the production settings and all of it at build time, right? So for all of these things you would have one build spec, and then you can pass in arguments at build time. So you would have a development build separately and a production build separately, but still I would advise the production build to be run on staging first and then promoted to production, rather than building straight to production and deploying to production. um, then we do tests, right? Yes, there's unit tests on our code. I know a lot of developers don't do this, myself included. Uh, takes a lot of time and energy to write unit tests. Uh, then there's code quality tests with SonarQube and stuff. So what this allows us to do is one of the best things in SonarQube that has helped me and my organization is it actually looks at your security vulnerabilities to make sure that you don't commit your uh, credentials or whatever the things security stuff into your repository or into your builds, because that's very bad. Although your repository is private or whatever, a common guideline is like a rule of thumb is always treat your application or your code as open source. So don't put anything private there. Just git ignore them, or do all of those things. Then there's this thing called vulnerability scanning. So when you build images, etc., there's Claire, there's Trivi, there's Snike that's working with Docker right now, that allows you to do vulnerability scanning on your images. And more often than not, you're going to see a lot of critical vulnerabilities in your Docker images. If you're using slim versions or buster versions or Jesse versions in Docker. So in Docker there are versions. So the smallest version is called Alpine, the flavor, where Alpine is a 2 megabyte Alpine is a 2 megabyte Docker image that has the minimum sort of like Linux functionality and all of it. So Linux kernel functions and all of it. So you can very easily run your node or whatever the things in Alpine. It's a very small image and it doesn't have any other libraries. So it won't have any vulnerabilities. Whereas if you start building your Docker image with something like Ubuntu or Jesse or Slim or whatever, they have GCC libraries and few other libraries that may have vulnerabilities which would sort of like detect via these things, and it would throw you errors saying that you have this many critical vulnerabilities, etc. So it's always recommended to go with the Alpine version and then install whatever the libraries that you want on top of the Alpine version to avoid critical vulnerabilities on your images. And then we can do integration tests. can do functional testing with Selenium and stuff. You can do cross-browser tests. So many tests I'm not going to talk about here. So many tools to do these things. I think you probably are familiar with many of those. Then we can do load tests with JMeter, artillery, etc. So if you're an architect and if you're designing an application, you're always going to go with start with the non-functional requirements, right? So one of the popular non-functional requirement for any application is like how many requests this application is going to serve. Uh, so to match it, we have to sort of like do a load test to sort of like see, like, this is our target is 1,000 requests per second, and with 1,000 requests per second under 2 GB RAM and 1 CPU, whatever. If this application meet that load? So we do the load test to verify that. We do regression tests to check whether the changes are affecting the old ones and all of it. And then after deployment, we do the use acceptance testing and all of those as well. I mean, there could be other types of tests as well, but these were the ones that I or my company and my team are using the most. Okay. Um, so in the CICD pipeline, again, right, this is how it works. So build, test, whether it fails or successes, you notify for success, and then uh, if it fails, you again do the changes, and then goes on like that. Um, so CICD tools, which allows us to do this entire thing that I talk about, right? If you're using GitHub, perfect. GitHub Actions is an excellent tool that you can use. It has so many options, so many actions you can do. It's very straightforward and you can do it very easily. If you're using something like GitLab, so GitLab has something called GitLab CI, which you have to install. You have to configure a little bit. You have to install this thing called runners on some other machines so that you can do the runs and all of it. If you have a Kubernetes cluster, easily you can run GitLab CI stuff as runners on Kubernetes. But GitLab CI is also pretty straightforward. You can configure a lot of things and get it running. I haven't used Atlassian Bamboo, but I have heard it's good. People who are using it, it has a lot of options as well. So Jenkins, right? So I've used Jenkins. Uh, I'm personally not a fan, but some of my friends are good fans of Jenkins. But I think Jenkins is a bit old now, and then there's so many things that you can do with Jenkins, but configuring it and all of it, I mean, it's too much configurations for me, to be honest. And there's the new one, Jenkins X, which works with Kubernetes, the whole cloud native way and all of it. Seems to be good. I have tried it once or twice, but then again, it's Jenkins, so I don't use it much. Circle CI, again, I think this is a paid one, if I'm not mistaken. I'm not sure, but I've seen Circle CI in action. I've seen in some projects, and Circle CI seems to be really good. Spinnaker, again, this is done by the Netflix guys. So back in the day, I think when I started Kubernetes in 2016 or 17, I can't remember. So back then, no CI/CD platform supported Kubernetes, only Spinnaker did. But today, that's not the case. A lot of the CI/CD pipelines support Kubernetes. So Spinnaker is also sort of like one of them. But Spinnaker was like the ones that supported Kubernetes early on. CodeFresh, again, a paid one, a very good experience. I've seen their demos. CodeFresh is also a good one. Tekton. Tekton is a Kubernetes native CI/CD pipeline. So you can basically configure all of these things within Kubernetes to do your CI/CD and all of it. So Tekton is a very good solution if you're 100% cloud native and you want to run your stuff on your own servers, basically. Like if you take GitHub Actions, etc., it's going to be running on GitHub servers. But Tekton, it would be running on your own Kubernetes servers. You can observe them, you can work with them and all of it. It's 100% Kubernetes native. So is Argo Workflows. I remember Kasun, my friend, did a demo on this in one of the Kubernetes meetups we had, I think last month or something. Similar to Tekton, it has a UI. Tekton is more towards GitOps. So you type the configs and then you push it and it automatically works. Whereas Argo Workflows has a UI, nice UI, where you can sort of like click buttons and do certain things on the UI, look at the status and all of it. There's another thing called Weaveworks, uh, Weaveworks Flux CD toolkit. So that also is similar to Tecton. It allows you to sort of like build your pipelines in sort of like a GitOps native way. Right. So those are the CI/CD tools. Um, this is like the full overview. It's quite a lot, really. Uh, you can see on the planning stage we have Jira, ServiceNow, etc. And for builds and all of it, you have a lot of things, Jenkins and the stuff that we spoke about. And for packaging, you have Docker and few others. Testing, and then again for staging and all of it, you have Rancher, Chef, Puppet, infrastructure side, all of those things. And you can observe this later on when I share the slide deck with you guys. Um, okay, so the next thing is monitoring. So this is going to be a very brief thing with monitoring. We are out of time as well, I think. Uh, because the next session, Aziz is going to dive into deep about monitoring and observability. I'm just going to touch the surface here because some components here come under CI/CD as well. So under monitoring, what we need to do is, so in the continuous deployment cycle, when we do the deployment, we would look at memory, storage, network. We are going to look at the logs. We are going to look at runtime security, like what are the things these people are doing in the, like for example, there are certain Docker images, if you don't get from the official site and from third-party vendors, they might be running Bitcoin mining scripts on your Docker images, right? That could be possible. So you had to take a look at the runtime security and see whether there's any, funny things are happening on your servers. You have to sort of like look if your application is restarting. Like the funniest thing is like, right, we tell that Kubernetes, if your application crashes, it automatically restarts. That's perfect. It gives us the availability that we need. But we need to know that the application restarted, right? It restarted probably because of an error. So we would never know that there was an error because Kubernetes keeps restarting it and making it available unless we set up monitoring and sort of like monitor how many restarts there are and what was the cause for the restart of the certain content. And then latency, where you can sort of like trace the latency with the microservices, how like we call this APM, application performance monitoring. So you can see how much time it takes to do a database call, whether your database calls or whether your database tables need any indexing or stuff like that, how much time it takes from one service to another service to talk to each other, how much time it takes for an entire domain request. What a domain request is basically is like when you do a domain request, it's going to talk to multiple microservices and then give you a result. So how much time an entire domain request takes, so stuff like that. So you need to monitor all of these things to sort of like find out where things are slow and or where errors are happening or where issues are going to get encountered, and then you have to fix those things. So the need for the continuous monitoring is what I just explained, so I'm not going to go through this. So the monitoring tools that allows us to do is the cloud native stack. Everybody screams Prometheus. So Prometheus is the one that allows us to basically monitor Kubernetes natively and look at our containers, how these containers are performing. Prometheus is huge in the Kubernetes community. And for everything, you can integrate Prometheus with it. There's a whole architecture with Prometheus, push and pull. It usually do the scrapes and all of it. I mean, read it later on. Then there's Grafana. Again, goes hand in hand with Prometheus, very popular. Gives us, Grafana is sort of like a front end for Prometheus, which allows us to create nice dashboards and look at all of these things properly. There's another one called CICD Falcon. Is it Falco or Falcon? I'm not sure. Maybe I miswrote this. Should be Falco, I think. So what Falco does is it is more focused towards security, runtime security specifically. So when your containers are running, it's gonna monitor your container processes and it's gonna see how many syscalls it's making, whether it's talking, whether it's doing any unwanted stuff, whether you are running it as a root user. It's gonna do a lot of security stuff. So like if your company has few security policies that you have to match, SysDig is something that you absolutely must implement. Fluentd again is a logging solution. So it sort of like streams your logs of your applications into a central server, something like Elasticsearch or somewhere. And then on Fluentd, you can actually set up metrics as well, like number of error logs that are being shipped. Like you can analyze the logs and do all of these things and set up alerts to that as well. Elastic Stack again, it has its own stuff, so you can have log speed, metric speed, and all of it, and can sort of like similar to Prometheus. You can have dashboards, you can set up alerts, you can store logs. It's an entire one solution. But I would personally go with Prometheus than the Elastic Stack for monitoring. It depends on users' preference and their requirements. Sentry is another tool I personally use, and this is also comes under application performance monitoring. So this allows us to look at the service latencies. It's more like an error tracking tool. Like for example, if like many of the front ends like React, Angular, all of these things, they don't run in a server, right? They would be running on user's browser. So when an issue encounters on user's browser, there's no way for us to know. Like a client or a user might be calling us and saying, hey, this is not working. But we can't really ask them to go into the console and give us a stack trace, right? Can't do that. So Sentry does exactly that. So when an error occurs on user's browser, it would ship that stack trace to a central place so that we can take a look and see what's going wrong. It also supports the server-side errors as well, but it's widely popular on the front-end side where you can very easily configure it so that you don't have to ask your customers to send the console log stack trace on their Chrome or whatever. Jaeger and Zipkin are tracing tools. It supports open tracing format. So basically allows us to sort of like ship our HTTP requests, the tracing IDs and all of it, so that it sort of like tracks like how much time it takes from one service to another service, the maximum time, the average time, and all of it. There are a lot of things that we can configure there. And then from that, we can identify, right, so this is the service or this is the function that's taking longer time to execute. Maybe we can fix that function or optimize that function, right? So these are sort of like the monitoring tools. And then you're going to go into deployment methods, and then we're going to be done with the presentation. So deploying applications, not specifically towards Kubernetes, but I'll be talking Kubernetes in context here. The Highlander method is basically you have the version 1 running, you would replace it by version 2. Just replace version 1 by version 2, and that's it. You're done with it, right? This is a common thing that a lot of PHP developers do with FileZilla and all of it. They would just open the FileZilla browser. On the right hand side there's a server, on the left hand side you have your application. You would just copy the files into the server and you're done with it, right? Even Java developers, they would sometimes do the jar is there on the server, they would just rename it, and then they would copy the new jar and stop the old jar and then start the new jar, right? And that's basically Highland, right? It's not recommended. Canary deployment. So this is a bit better. So here what happens is that you have 3 nodes running now, and you update one application, and then because this is a load balancer that's basically routing the traffic equally, so 60%, 66% of the routing requests are going to V1 and 33% is going to V2. And you can observe it for a while and see if this is running into any issues or whether users are running into any issues or stuff like that. You can monitor it. And if everything is okay, you can go ahead and update the other 2 as well. This is called canary deployment. It's a safer way of updating things. But it's a bit manual, because now say you update this and then you wait and you observe and then you make a conscious decision to update the other 2. Rolling update is different. It's automatic. So in this scenario, rolling update, as you can see, you would update the first one with v2, and then when this one becomes healthy and ready to serve, the next one, you start updating the second one, and when that also becomes healthy and ready to serve, the third one will get deployed. Now there's a problem with rolling update. So it only looks at application runtime healthiness. So basically, if the application starts serving on whatever the port that you have defined, and it's ready to accept requests, it would deem this as healthy, right? But there's a little problem here. Like, for example, let's say that there's a specific URL, like say get user information. That particular function is breaking on application. So at runtime, at the start time, and when the application is ready to accept requests, it doesn't know that that particular function is buggy, right? So it's gonna deem itself as healthy, and then it's going to start the process would be there. So everything will get updated to v2, and then all the v2 applications, now users cannot get the user information because the get information function is buggy. But in this scenario, because v2 is running for some time, we know if users try to access the get information URL here, this app is going to fail, and we would know that, and we would know that, okay, there's a bug with the application, we need to fix it before updating these two. So in that sense, it is safe compared to a rolling update. But rolling update is easier with Kubernetes. This is the one that ships default with Kubernetes. If you don't have to configure anything, it just updates, right? Then there's another thing called blue-green. So there's another thing called blue-green. So in the blue-green, what you did was, here what we always did was we updated the existing set of applications, right? Here that's not the case. We would have two sets of applications as two deployments. So you have the version 1 and version 2. All we do is we change our load balancer settings to point to the version 2 instead of version 1. And if there's a problem with version 2, you can always point your load balancer into version 1. So that's what we call by blue-green. So it's sort of like double the resources, but it's more safer now, because version 1 is running, and then if something goes wrong, you can always point back to the other version, right? It's sort of like a roll backup policy sort of a thing. There are other deployment methods as well, like the A/B testing method. So in the A/B testing method, some of the users will get certain things, or like some users would get one version, another user would get another version. And then there's another one called shadow deployment or a dark launch. So what the dark launch would do is basically you would have the version 1 running, and then you would deploy version 2 behind the scenes, and all the requests that goes into version 1 is mirrored into version 2 behind the scenes, so that you can monitor how the version 2 sort of like performs and all of it. So dark launch is something that you would do when you are doing a major upgrade, like you are doing major version 1 into a major version 2, where you are deprecating a lot of APIs, but you want to still handle integrations and all of it. So dark launch is a way to go there, so that you can actually stream some live traffic into the new version, and then see how it performs without affecting the existing users, right? Feature toggle is how Facebook and all of these things work, where certain users, depending on their metadata or their location or whatever, you would point them into different versions of the application, so that they can have different features. So that's deployment methods. So actually these stuff, there you go. It's sort of like a nutshell here, and you can see the option zero downtime and all of it. And then the cloud cost also, like blue-green has the highest cost, and so does the shadow, right? And also like complexity of setting up. You can see the shadow, A/B testing, blue-green, all of these are hard, right? But the recreate and the ramped one and all of it, ramped is basically rolling updates. So those are really easy to sort of like implement. So we can all study this also a bit more when I share the slide deck with you guys. Uh, so That's it basically. So we talked about CI/CD, so I just wanted you to think about this one. So we are talking about deployments with zero downtimes when there are and all of it. So we were specifically talking about application, but we never spoke about the database layer, right? The data layer, the persistent layer. So how would that work out? Like imagine a rolling update situation or a canary deployment where this is version 2 and where this is version 1, and if this is going to do a database change, it's going to affect these two as well, right? So you have to be careful there. So when you do database migrations, there's a safe set of rules that you need to follow. Like for example, never do column renames, always add a new column. Do proper migrations and all of it, so that your new database structure is always compatible with the old database structure, with the old versions database structure. That otherwise, something like this is gonna screw you up real bad. Even this, even if you want to roll back, you're screwed because version 1 is not working anymore because your database is corrupted. It's not supporting by this. So always keep in mind, database is critical. Do database changes on new versions so that it supports the old version. So don't do any breaking changes. So I think that's pretty much it. So on the next one, Aziz is probably going to talk about observability tracing as this whole concept called service mesh, chaos engineering, and all of that, and how WSO2, Ballerina, and all of those things also come into play. Uh, yeah. So that's what's in store in the next session. Thank you. So do you have any questions for me from the session? I'm happy.
So we'll open up for the questions. So you can post your question on the any questions? Yeah, one more question was posted. Yeah, sure. We'll share the PDF presentation. So, Nilesh, I have a question now. If you take the industry trend, like, OpenShift, they are recommending either in a bare metal or virtualized environment for the deployment perspective. For example, on top of VMware or RHEV, you can deploy the OpenShift on top of virtualization or bare metal. But at the same time, like, the vendors like Rancher, they deploy directly on the bare metal servers. So in terms of performance and the isolating issues, what is your recommendation?
It's always good to go with virtual machines because you can always, there's so many things that you can do with virtual machines rather than bare metal. I think even Rancher doesn't really recommend bare metal, right? Rancher also supports bare metal and virtual machines. It depends on a scenario. So basically, when you go with bare metal, it's more towards edge scenarios where you don't have much resources and you go with bare metal. But when you go with virtualization, virtual machines, you can always, there's so many things that you can configure there, and there's a lot of control that you can do where, if bare metal screws up, you are screwed up, right? But in a virtual machine, there's a control plane that you can always do something about it. So that's something. And also, like, I know, like, guys like Weaveworks, etc. People are working towards even bringing merging bare metal and virtual machines together to sort of like give a seamless sort of like a Kubernetes experience together. There are projects like Firecracker that allows you to do that. So there's so many things that you can do, but my personal input would be to go with virtual machines unless there's no option that you have to go with bare metal.
There was one question posted. Is Terraform also related to orchestration?
No, it's not. So Terraform is basically so Terraform and Ansible, basically these two are like go hand in hand. So what these are doing is like this. This is called infrastructure as code. So what this does is basically like when you create cloud resources or stuff like that, like let's take AWS, you're creating a VM. There's the easiest way to do that is log into the AWS control plane, press a couple of buttons and create the VM, right? But that's easy for you, but it's very hard to, sort of like in an enterprise manage it. So rather than that, it's better if you can write a Terraform script, which, write the entire VM creation process as a Terraform script. We call it as infrastructure as code. So from that, you can actually do auditing, you can check security and all of these things, you can configure these things and you can push it. And then if somebody else wants to come in, they can read it, they can edit it. You can manage your cloud state using this script, the Terraform script, which is like the absolute truth. Uh, so that's what Terraform and stuff does. So using Terraform so what Terraform does is basically it allows you to create cloud resources. What Ansible does is it allows you to SSH into your Linux environment or whatever, and then install libraries and stuff like sudo yum install, etc. Set up nginx or stuff like that. That that's done with Ansible. Basically, if you want to set up an nginx server in AWS, you would write a Terraform script to create a VM, the firewall, open the firewall rules and all of that using Terraform. And then you would write an Ansible script to SSH into the VM that you created. Right? And then this is sort of like going to be a template. So you can easily spin up an Nginx server anywhere in AWS, not for this particular project, but anything, just one with one single command after you create that template. Nothing to do with orchestration.
One last question was, Nilesh, how does distributed systems fit into this?
So distributed systems like microservices, right? So Kubernetes is a platform that allows you to run your microservices. So how you manage the distribution of data and how all of these things, like how they talk to each other, that's up to you to figure out, and that's up to you to architect. What Kubernetes allows you to do is basically give you a platform to manage your microservices and maintain their availability, state, all of those things in a single control plane. So scale them, service discovery, all of it, handles within the Kubernetes itself. Like basically your distributed system, you can tell Kubernetes, run my application and then scale it to 2, scale it to 5, whatever, it would do that. But the distributed part, you probably have to write it on your code and figure out how to do it depending on your requirements.
Okay, so let's wind up. So very good evening to everyone. So it is with great pleasure that I'm delivering the vote of thanks. Firstly, on behalf of IT and Computer Engineering Sectional Committee, we wish to express our sincere gratitude to ISL President, Secretary and the staff. So our special thanks to Mr. Nilesh, who has given his precious time to conduct this event. And we are thankful to him for sharing his immense knowledge on evaluation of application development from app services and API to microservices. Obviously, we will be having a final session on this, which will cover a security perspective on these microservices architecture technologies. So once again, many thanks, Nilesh, to enable this evening to have a successful event. Also, I would like to thank our organization team of IT and Computer Engineering Sectional Committee for helping us to arrange this public lecture. We are organizing this kind of events to uplift the IS in all aspects. So finally, I extend my big thanks to all of the participants who made this event successful. So thank you. Have a pleasant day. So any feedback, it's welcome. So thank you so much. Thank you so much, everyone. Thank you, Nilesh. Thank you.